Evidence number 2, different radioisotope ages. Well, the 4 major radioisotope dating methods used on rocks are potassium to argon, rubidium to strontium, uranium to lead, samarium to neodymium. Now, when most geologists do their studies, they only ever use 1 or 2 of these methods on their rock samples. Why? Because they say, well, whatever clock we use, we should get the same results. Whether we use the uranium method or the potassium method, it doesn't matter. Because the rock only has one age, and these clocks are all supposed to agree with one another. Therefore, they should all use the same ages. And so they only ever do 1 or more dating methods on the same rock samples. And if someone ever wants to repeat the work, they usually collect different samples to use a different method. So we said, okay, we'll get smart. We'll use all 4 methods on the same rock samples to really see whether these clocks agree with one another. And we also use the superior isochron method that I talked about earlier. Why is it superior? Because instead of using 1 sample, you use 5 or more samples. And in many of our studies, we used up to 20 samples so that nobody could accuse us of being lied on with data. And that's very important. The more data, the more ability to get tighter statistics in our results. And that's exactly what we found. So I want to show you 4 rock units from the Grand Canyon. First of all, there's this rock unit where the molten rock was squeezed like toothpaste between sedimentary rocks. It's called a sill. And the rock is a diabase, which is like a basalt. And these are the results that we obtained. The potassium-argon result was 841.5 million years. The rubidium-strontium, 1,060 million years. The uranium-lead was 1,250 million years. And the samarium-neodymium, 1,379 million years. Do any of those agree with one another? Maybe there's an option E, none of the above. And interestingly, with some of these results, we actually took a single sample and separated it into its constituent minerals and analysed the individual minerals. So you would think the individual minerals together in the same rock should always give the same age with all the different methods, but they didn't. There's more. This is a series of basalt lava flows deep in the Grand Canyon, in the eastern Grand Canyon. Here's the results. Potassium-argon, 516 million years. Rubidium-strontium, double that at 1.1 billion years, or 1,111 million years. And samarium-neodymium, 3 times the potassium-argon at 1,588 million years. That's not very good hitting the bullseye, is it? The samarium is 3 times the size of the potassium-argon result. Not very good. We go to another rock unit, got a strange name, amphibolite. It's actually a metamorphosed basalt, ancient lava flows that were heated up and changed. Their mineral composition changed. And guess what? Rubidium-strontium gave it an age of 1,240 million years. Uranium-lead, or lead-lead, gave 1,883 million years, and samarium-neodymium, 1,655 million years. Now, you don't have to know all the technicalities to see that those numbers are not the same. They're not even close. And then there's a granite, the Earls Chasm granodiorite, a type of granite in the Grand Canyon. And the rubidium-strontium gauge an age of 1,512 million years, the lead-lead 1,933 million years, the samarium-neodymium 1,664 million years. Again, a great variance in these results. Now, there were some interesting patterns. We need to understand that these multiple radioisotopes from these 4 rock units always disagreed, always. And yet each of these rock units represent a single unique geologic event, the formation of this sill, or the metamorphosis of those lavas, the eruption of volcanic lavas, or the crystallization of a granite. A unique one-time geologic event. So it should have had the same age with these clocks, but they weren't the same. So if these radioactive clocks were accurate, always ticking at the same rates that we measured today, each clock should have given the same age, but they didn't. Therefore, the conclusion we come to is that each radioactive clock must have ticked at different and faster rates than today to give the different ages. Let me illustrate what I mean. For example, that Cardenas basalt. While the potassium-argon clock ticked through 516 million years, the rubidium-strontium clock was ticking more rapidly through 1111 million years, and the samarium-neodymium clock was going even faster and faster, ticking through 1588 million years. Now, I'm using the millions of years only in the sense that that's the numbers that come out of the equations. I'm not saying they're real millions of years. All I'm saying is that's relative to one another. The older age means the clock had to go faster and faster than the younger age for the two clocks to be reconciled. Was there a pattern? Yes, there was. Is there a factor, the underlying factor that we can determine? Yes, because if there's a pattern in these results, and there are patterns, that means there's a systematic process going on that would explain this accelerated nuclear decay. So if we look at some of these results, you've got the diabase sil, and notice that the potassium is younger than the rubidium, the same in the Cardenas basalt. The potassium is younger than the rubidium. The potassium has a shorter half-life, it decays more rapidly and it gave a younger age. The rubidium-strontium, which decays by the same beta decay process, gives an older age. That's interesting. And notice, rubidium-strontium decay by the beta process, which I don't have time to explain, and uranium and samarium decay by the alpha process, and the alpha process always gives older ages than the beta process. Now you see, if this was a random thing happening, you wouldn't have those patterns. We see the same in these other two rock units. The rubidium is always less than the uranium, the beta is always less than the alpha, the uranium and samarium. And that's what we found. The uranium and samarium neodymium ages, the alpha ages, are always older than the potassium, argon and rubidium, strontium, beta decay ages. And sometimes the longer the present half-lives, that's the slower the decay rate, the older were the ages. So rubidium, which had a slower decay rate, was always older than potassium, which has a faster decay rate. And we can also look at the atomic weight. And again, we find that the heavier atoms always give older ages than the lighter atoms. And therefore, there's a relationship to these ages between the decay rate and the size of the atom and the type of decay. We concluded that it has to do with the binding energy of the nuclear forces that hold the nuclei together. That you only have to make and theoretically you can show you only have to make a small change and you will accelerate nuclear decay. And I don't have time to go into that tonight. When all four major methods were used to date the same samples from the same rocks, they invariably yielded different ages. And these different ages can be explained if these radioactive clocks ticked at faster rates in the past, at different faster rates than today's measured slow rates. And so we have to conclude that these different radioisotope ages from the same rocks are evidence of accelerated nuclear decay, matching what we discovered from the helium leaking out of those zircon crystals.